Hi everyone. So today we're going to talk about convergence of Fourier series, when that happens, and then we're going to talk about the space of functions that the complex exponentials form as a basis. And once we have that and the inner product, then we'll know a way to recast a lot of the structural results that we've proved already, but in the language of linear algebra, which is a useful and much shorter way of understanding what's happening with a lot of these formulas. It will also prove that the Foia approximation is the best possible approximation that you can make to a function given the complex exponentials as the basis for expanding the function. So here's the big question that we have so far. We know that if we have a function that looks like f of t, and that f of t can be written as the sum from n equals minus n to n of Cn e to the 2 pi I n t. Then if a function can be written that way, then we could write down that Cn was equal to the integral from 0 to 1 of f of t e to the minus 2 pi I n t dt. That is, if f can be written in this way, then the Cn's can be determined uniquely using this integral formula. The bigger question is, can I extend this formula to infinity? And if I do, can I use it to approximate? What sorts of functions can I use it to approximate? So the object of our questions is going to be an infinite Fourier series. So let's write down an infinite Fourier series. So just like usual, when we write an infinite sum down, we really mean a limit of a finite sum. So if we took the limit as n goes to infinity of the sum from little n is equal to minus n to n of Cn e to the 2 pi I n t, where the Cn's are generated by the formula the integral from 0 to 1 of f of t e to the minus 2 pi I n t dt. There's a shorthand notation for what we've just written here, which is the sum from little n is equal to minus infinity to infinity of Cn e to the 2 pi I n t. So these things are equal. And again, when we see infinities in limits of sums or limits of integrals, we always think them as representing some sort of finite limit or a limit of a finite thing so that it makes sense to write down. So this object right here, we have some questions about it. And what we really want, if we've generated the Cn's using the Foia coefficient formula, what we really want is that this is equal to f of t. This is what we'd love to have happen. We want this. But in order to equal f of t, two different things need to happen. First, the sum had better converge whenever I put a value of t into it. And second, it had better converge to the function. So let me rephrase that. Suppose that we had an f of t, which is some function, and we used it to generate something formally that looks like an infinite Fourier series. So over here, we have the sum from little n is equal to minus infinity to infinity of Cn e to the 2 pi I n t, where we've used the formula Cn is the integral of f e to the minus 2 pi I n t dt to generate the coefficients. Two things need to be true in order for f of t to be equal to this series. The first thing is it had better be the case that if I plug in t naught to get the sum from n is equal to minus infinity to infinity of Cn e to the specific function 2 pi I n t naught, that had better converge. After all, at this point, it's just a series of numbers that are adding up. It's complex numbers, but they work the same way as real numbers do. The second question is, if it does converge, it had better converge to f at t naught. If it does converge, then the sum from n is equal to minus infinity to infinity of Cn e to the 2 pi I n t naught had better be equal to f of t naught. The first question says, when does the sum converge? The second question says, whatever it converges to, it actually reproduces the behavior of f at that point. And only when both of these conditions are true can we say that f has an infinite Fourier series that represents it. Now, using the language of partial sums, we can rewrite those conditions into something that we're more familiar with. And that is to say, what we really want to be true is that the limit as n goes to infinity of the sum from little n is equal to minus n to n of Cn e to the 2 pi I n t naught exists. In shorthand, we might say that the limit as n goes to infinity of Sn exists, where Sn is called the partial sums. Okay, so these two things are equal to each other. And the second condition says not only does the limit exist, but the limit equals to what we want it to. That the limit as n goes to infinity of Sn is actually equal to f of t naught. Two different conditions. One, the limit exists. Two, the limit is equal to the function at that point. So Fourier series have an expansion theorem that looks a lot like the expansion theorems that we've already done, with one condition that we can loosen, actually. So remember that in a lot of the problems we've been dealing with, the functions have been not continuous, but piecewise continuous, which is to say we allow jump discontinuities to exist in periodic functions. And we allow jump discontinuities to exist in the derivatives as well. For example, in the triangle function, the derivatives have a jump discontinuity because in the triangle function you go from slope 1 to, say, slope minus 1. And that's a function that has a jump discontinuity in the derivative. So what the theorem says about when you're allowed to use Fourier series is actually very open. So here is the big theorem. So first we're going to set the conditions that f needs to satisfy. So we're going to assume that f is piecewise continuous and periodic, and that the derivative of f is also piecewise continuous. Then, if f is continuous at some point t naught, then f of t naught is equal to the limit as n goes to infinity of Sn evaluated at t naught, which is equal to the sum from minus infinity to infinity of Cn e to the 2 pi I n t. Or in the language that we're going to be using going forward, we could equivalently write the sum of f hat n e to the 2 pi I n t. So there you go. That's when we can use a Fourier series. F is piecewise continuous, f is periodic, and f prime is piecewise continuous. Now, all of the functions that we've dealt with so far have been periodic on an interval of length 1. The machinery that we've built is actually very easy to modify so that a function could be periodic on an interval, say, of length t. Let's be specific about what these terms mean. Piecewise continuous. What that means is that you have at most, finite number of jump discontinuities. That is no asymptotes. We're still not allowing asymptotes to happen here. And then by periodic, we already know what that means. Periodic means that f of t is equal to f of t plus capital T for some t. Having the derivative piecewise continuous means that the derivative satisfies the piecewise continuous property, which is that the derivative is continuous except for possibly a finite number of jump discontinuities. So of the functions that we've looked at previously, we can actually classify what sorts of functions these are. So when we looked at something like the square wave, so the square wave was piecewise continuous because the square wave took on values of -1 and 1. And it's continuous in all the pieces, and these gaps right here where it leaps up and down, those are the jump discontinuities. And the derivative of the square wave is 0 everywhere it's defined because the function is always flat. So f prime is also continuous because the derivative is 0. And so that's why the square wave can be approximated or expanded in terms of complex exponentials using a Fourier series. The triangle wave, well, that function is continuous because we got something that looked like this. So f is continuous. And f prime is piecewise continuous. Because f prime is going to have values that look like this. If this is f, then f prime looks like this. It has slope 1 and then slope -1. It has slope. So f prime is going to look like this. It has slope 1 and then slope -1 and then slope 1 and then slope -1. So the derivative of a triangular wave is a square wave. So f is continuous and f prime is piecewise continuous, and that's why the triangle wave could be approximated with a Fourier series. So now that we know that Fourier series converge to functions, so essentially what that theorem says is that as long as f is nice, so if f is nice, and remember by nice we mean periodic, continuous, piecewise, and derivative continuous piecewise. So if f is nice, then f of t basically is equal to the sum from n is equal to -infinity to infinity of Cn e to the 2 pi I n t, where Cn is the nth Fourier coefficient, which you get by integrating from 0 to 1. In the case that we're thinking about where the complex exponentials have been normalized to have period 1. Now, once we know this, once we know that the function is equal to that Fourier series for all t in the interval from 0 to 1, then we can start talking about using the complex exponentials to build up a vector space of functions. So we can recast what we've already done in the language of linear algebra. Remember that before, what we showed was that Cn was equal to this integral formula by doing a bunch of algebra and then integrating an equation and noticing that a certain integral collapsed into nothing. Well, we could have started from that position. The fact that f of t, that any f that satisfies these properties, can be approximated with a Fourier series is going to be the backbone of constructing the vector space that Fourier series are the natural object for. So here's the first observation that we can make about complex exponentials, and I think this came up in passing in an earlier video. So let's look at the integral from 0 to 1 of e to the 2 pi I nt times e to the -2 pi I mt, where n and m are not equal, because I don't really want to have a 0 up in the exponent of this function. If you do that, what you end up with is the integral from 0 to 1 of e to the 2 pi I n minus mt dt, which integrates to 1 over 2 pi I n minus m times e to the 2 pi I n minus mt evaluated from 0 to 1. And since the n minus m the n and m aren't equal, it's okay to divide by n minus m. That's actually why we have to specify that n and m are not the same number. Now, you have to remember that e to the 2 pi I is equal to 1. So this is a big fact. E to the 2 pi I is 1. And if you don't see it precisely why that must be true, I want you to write down a unit circle and imagine what it is that e to the 2 pi I is actually representing on the unit circle. Or, if you like, you could take e to the 2 pi I and you could convert it into sines and cosines and see why that must be true. Now we can go one step further with complex exponentials that look like this, and we can say e to the 2 pi I times any integer k is also equal to 1. All that the k is doing is wrapping the function around the circle k times until it lands back where it started again. Since that is true, when we do this evaluation, what we end up with is 1 over 2 pi I n minus m e to the 2 pi I n minus m from plugging in t equals 1 minus e to the 0 for plugging in t equals 0. Now, e to the 0 is 1, but e to the 2 pi I n minus m, well, n minus m is an integer. So e to the 2 pi I n minus m is also 1 by this fact right here. So this is e to the 2 pi I n minus m times 1 minus 1, which is 0. So this integral is nothing. This actually guides our selection of an inner product for the spaces that these functions build up. So what space of functions can we use, knowing that we have the integral from 0 to 1 of e to the 2 pi I n t times e to the minus 2 pi I mt dt is 0. Well, what if I let an inner product be defined by f and g when I take their inner product? I'm going to do the integral from 0 to 1 of f times the complex conjugate of g. I have to use the complex conjugate because the space of functions I'm working with is a complex valued space of functions. And so if I'm working with complex numbers and I want the inner product to do what it's supposed to do, because the I is floating around on the inside of everything, if I want the norm expression, the absolute value expression to work correctly, I have to conjugate the second entry when I take the inner product. Okay, so this is, say, an inner product on some space of functions. And with respect to that inner product, e to the 2 pi I nt and e to the 2 pi I mt are orthogonal. That is, as functions with respect to this inner product, e to the 2 pi I nt is perpendicular to e to the 2 pi I mt. That's great. Even better, using this inner product formula, we can show that the absolute value, or length, of e to the 2 pi I nt is 1. So these are unit vectors. So not only is e to the 2 pi I nt perpendicular to e to the 2 pi I mt, but furthermore, the length of e to the 2 pi I nt, which remember is just the inner product of a function with itself, and we can put a square here so we don't have to deal with square roots. If I compute this, what I get is that the length of e to the 2 pi I nt, well, these just cancel in the integral, and you just get the integral from 0 to 1 of 1, which is just 1. So not only are the family e to the 2 pi I nt all orthogonal to each other, their lengths are all 1. So the family e to the 2 pi I nt from 0, not even 0, from minus infinity to infinity is an orthogonal family of unit vectors. Even better, we already know what sorts of functions can be expressed in terms of these complex exponentials. All of the conditions on f that we've already established can be written briefly like this. F is periodic and piecewise C1, which means piecewise the function is continuous with a continuous derivative. Then any f that builds up or that has this property, we say then f has a Foia expansion. In terms of e to the 2 pi I n t, which is to say e to the 2 pi I n t is a basis for the set of functions f that are piecewise C1. E to the 2 pi I n t is a basis for all such f. So every f that is periodic and piecewise C1 has a unique expansion in terms of these complex exponentials. And since we have an inner product, not only is that a vector space, it's an inner product space. So there's an easier way to remember the expansion formula. And it looks like this. If we have the inner product of f and g being equal to the integral from 0 to 1 of f complex conjugate of g dt, then f can be written as the sum from n equals minus infinity to infinity of the inner product of f with e to the 2 pi I n t, e to the 2 pi I n t. There's not even a denominator in this vector projection because all of the complex exponentials are unit vectors. So this thing right here is the core idea of Foia expansion, thought of from the linear algebraic perspective. We can say a little bit more about the types of functions f that I can do this to, because it turns out that Foia series can be used to model a lot of functions that are not even functions in the way that we think about them. So the most important space of functions in all of analysis is called L2. And we're going to be looking at L2 functions on the interval 0 to 1. The L stands for a guy named Henri Lebesgue. And so Lebesgue came up with a theory of integration that makes all this work. And the way that you define functions in L2 is you say a function is in L2 if it has finite energy. A function f on the interval from 0 to 1 is in L2 if f has finite energy. And it's not energy like a physicist thinks about energy, but it's a constant multiple of that. So we define the energy of a signal, or the energy of f, is equal to the integral from 0 to 1 of the absolute value of f of t squared dt. And so to say that a signal has finite energy means that this integral is finite. Now you could also use the absolute value instead of the absolute value squared, but then you lose the connection to physical energy the way that a physicist thinks about it. And you also lose certain features that the space of functions is going to have, namely that Foia approximations are the best approximations. So this set of functions, that is the functions L2 of 0, 1, where L stood for Lebesgue, and we say that f is in L2 if f has finite energy in this sense. And we've got to be a little bit careful here because this dt, this is not regular old Riemann integration. So that's not really going to matter much to us, but we want to be able to handle things like impulse functions and functions that have an infinite number of discontinuities. And so in order to do that, the dt here is secretly Lebesgue integration. And as you go on to higher level mathematics classes or graduate school, you're going to have to probably develop the machinery to show how that works. In practice, we don't need to know that much to develop the theory. And in application, it doesn't really come up very often that you need to know that a function is Lebesgue integral versus regular old integral, the way that we think about it from Calculus 1. I just want you to know that there's a theory of integration that contains all of Riemann integration, but a lot more things that are not even really functions, called distributions, and all of this theory also works for those. So for example, you could take a Foia approximation of a Dirac delta function, if you know what that is, which is pretty bizarre. So it turns out to be the case that the L2 functions are precisely the space of functions for which the complex exponentials are a basis. So remember, L2 of 0, 1 is the space of functions for which the integral from 0 to 1 of the absolute value of f squared is finite. And for those functions, e to the 2 pi I n t is an orthogonal basis of unit vectors. Which is pretty amazing. So why do we care that we have an orthogonal basis in this linear algebraic machinery? Well, it turns out to be the case that once you know that you have an orthogonal basis with respect to this particular inner product, then automatically, remember that we're writing down f is equal to the sum from n is equal to minus infinity to infinity of the inner product of f with e to the 2 pi I n t times e to the 2 pi I n t. Automatically, if I clip this off at a finite number n, okay, so f is equal to this. What if I just want to approximate? The fact that the complex exponentials are a basis for the space L2 that all this lives in says the following. For any n, for any capital N, the sum from n is equal to minus n to uppercase N of f e the 2 pi I n t inner product e to the 2 pi I n t is the best approximation. We should say the best least squares approximation. That you can't do any better using the complex exponentials as the basis for building this thing up. This is absolutely the best. So the Foia approximation, the finite Foia series, is the best harmonic decomposition of a function that you're going to find. Okay, so we covered a lot of ground today, and the upshot is the following. First, we talked about a convergence theorem for functions f that have Foia series, and it said that if f is C1 piecewise and periodic, then f is equal to its infinite Foia series on 0, 1. Okay. 2, we showed that e to the 2 pi I n t, that family of functions from n is equal to minus infinity to infinity, is an orthogonal basis of unit vectors for all functions that have the property that the integral from 0 to 1 of the absolute value of f squared dt is finite. That's an even bigger expansion theorem because that means that we can go way beyond C1 piecewise and periodic and say that there's an enormous family of functions that envelop that are also subject to Foia expansion. So these two ideas are connected. You sort of have an algebra calculus idea in the theorem, and then you have this linear algebraic geometric idea in the second point. And these two perspectives can be used to switch back and forth. And the sort of information that you might find in one way of thinking could be useful, or you could switch to the other way of thinking and get different information. This is related to the idea of looking at the time domain function f or the frequency domain function f hat. That knowing the coefficients of f is essentially identical to knowing the function f, but different information is available from each setting. So now that we've built up all this machinery, the next thing that we want to do is to show how we can take the ideas that we've developed and use them to solve a particular differential equation. We already looked at the heat equation as an inspiration for where Foia series originally came from. So what we're going to do is we're going to actually solve the heat equation using Foia series. And in the course of solving the heat equation, we're going to find that the system itself that you're solving determines something about the structure of the Foia coefficients. And in the setting of electrical engineering, that's called impulse response. And the same sort of ideas also apply to mechanical systems or heat-driven systems. So there's another component to this that we haven't talked about yet, which is if you take a Fourier series and you try to use it to solve a particular equation, the system that you're solving also contributes information to the nature of the Foia coefficients. And the natural behavior of the system is something that we can actually isolate and tease out. In a lot of applications, that base response turns out to be of utmost importance in understanding how a system is going to respond to inputs. So the next big thing we're doing, to reiterate, is we're going to look at the relationship between the input and the system and the outputs, what that relationship is, and how the Fourier expansion of a solution can give us access to understanding what's going on in the connection between the input, the system, and the outputs. All right, so this is my favorite kind of math of all time. I hope you guys are finding it interesting. I think this is a spectacular achievement, and I really think it's the secret language, in some sense, the secret language of the universe. The fact that we can take signals and pull them apart like this into constituent functions that are easy to understand underlies some of the greatest mathematical advances of the last 300 years. All right, so keep plugging, and I'll talk to you later.